noetherian formal scheme. So R was noetherian ring. I ideal. And so I gave three definitions of the same K-theory, which is like my version of nuclear K-theory. So the K-theory of nuclear models, which is slightly different from the original one. So
it's slightly different in the sense that one contains another.
yes, my K-theory contains the original one. Yes, and but in fact, it will turn out in the end that the K-theory, for example, is the same. And
so for your purposes, they are the same.
In terms of invariance,
yes,
yeah.
but DG well, stable infinity characters are not only for computing.
Certainly, yes.
The other ideas of advantages and all that.
Well, I would say that my version is more natural just because it is registification of the completely standard case, which is just complete derived categories, and their version is registification of the category of solid modules, which is well, first you need to build that category and then make its registification, which is
again, which category is bigger?
My category is bigger. Yes. Okay, so the third calculation was nuclear. Let's just call it nuclear tilde to distinguish between the two versions. So first definition was that this is the dualizable inverse limit of derived categories of R mod I-adic. And this, yes, here I'm not considering any symmetric monodal structure, so this can be considered as a kind of non-commutative definition.
In the sense of non-commutative. Yes. Non-commutative geometry is understood as science about stable.
Yeah. Well, normally about small stable infinity categories, but they are different too. Yeah. So second definition, which is also non-commutative, actually, is that this nuclear category is the dualizable internal home from the I-complete or equivalent I-torsion derived category of R to the derived category of R. And home is R linear, and this is internal home in the symmetric model category of R linear dualizable category. So this is much more complicated than the usual internal home in the presentable world. So both of these, the first and second version, the definitions are non-commutative. And the third definition is commutative because it defines this category as symmetric monoidal category. So this is registification of the usual I-complete derived category of R.
And when we say commutative, this refers to the fact that we consider the symmetric monoidal category.
Yes. Yeah, we include
or it's a category of something.
Yes.
And at this tensor structure, is it clear that it exists one in one and two?
Well, from the second, you need to do some work, maybe a little bit, but from the first, yes.
Can you just pull back by the back?
Yeah.
Competing from something like this.
Well, I would say that if you define it as a limit, then all of these categories have symmetric model structures. Then yeah. I mean, you still need to be slightly careful because it's a dualizable limit, but it can make sense. Yeah. Okay, so I will actually explain like in more detail how this registification works, but a little bit later. But First, since we already discussed the dualizable inverse limits, I want to explain. So I want to formulate more precisely the statement that this dualizable inverse limit is well behaved. So, I mean, roughly speaking, we saw that in many cases, dualizable inverse limits are horrible and uncomputable, or at least they don't have good properties, like they don't compute with, like you don't have commutation of kernels with sequential colimits and so on. So in general, if you take a random inverse sequence, the dualizable inverse limit would be uncomputable, and you don't have a chance to compute any of its invariants. But here the situation is much better. And I want to explain what does it mean. That so first, let me formulate a precise statement. In this particular situation, and it's actually quite a difficult statement, that the functor from the naive inverse limit, like the usual inverse limit, I mean, of this countable derived categories of R mod I to the n. I mean, I'm just taking out of represented objects. So I'm taking a functor from this category to the inverse limit of countable Clausen categories of the same rings R mod I to the n. The statement is this functor is homological epimorphic. So both of these categories are small, and so the notion of homological epimorphism makes sense. Again, it means that after taking its completion, we get a closed functor. For proof that the right adjoint is fully faithful. And in particular, it means we have some of the sequence 0 to this nuclear tilde, the completion of R, to int completion of this usual usual limit countable derived categories to the int completion of the usual limit of counting categories. And okay, remark. I mean, this naive inverse limit of derived categories, countable ones, or the same for the whole derived category. This is just the familiar category of I complete. Our modules again take omega 1 objects. This is kind of familiar. If you take naive inverse limits, but yeah, but here we have this inverse limit of Calkins, which is quite complicated.
Sorry, so just when you say is that expression 0?
Sorry?
Sorry.
Yeah. Show the exact sequence. So in particular, this is essentially surjective, which is quite non-obvious. Yeah, and just to explain why this is really non-trivial, so just an example. So I mean, being homological epimorphism includes the statement that this functor is essentially surjective up to direct summons. And so, just an example: take any collection, any objects, like perfect objects. So any sequence Mn in perfect modules of R mod I to the n, and then we can form an object like Xn in the limit of Clausen categories. Where Xn just the direct sum of pullbacks, you take direct sum of let's say L relative to M, you take this ML and pull back to R mod I to the n. Derived. And so these guys, I mean, the difference, so you don't get an object of the inverse limit of like derived categories, but they're compatible with each other up to finite rank, so up to a perfect object. So in particular, such
So who and who are
I mean that like xn plus 1 base change to R mod I to the n. So like it projects onto xn. So I'm sorry. I mean it embeds in okay. It maps to xn like at a direct sum, but the difference between them is perfect. Yeah. So let's say that whole this map is perfect. It means that in the Calvin categories they're compatible with each other. So you get a well-defined object in the limit of Calvin categories, but there is no obvious lift of this object to the limit of actual derived categories. Yeah, I mean, this theorem applies. It implies that at least up to direct summons, such an object can be lifted to the usual inverse limit of derived categories, but like, there is no. I don't have any constructive proof of this fact. I just I can prove it using the general theory, but there is no explicit way to. Yeah, but I mean, in particular, it will be important for the computation of K-theory just to know that this particular object can be lifted to the inverse limit of derived categories. Okay, and so yeah, this will be the important property.
So the claim is that it's so important, as you said, the sequence of cells
yeah, limit of
and then your theorem implies that it can be lifted up to the
direct summons, yeah, can be lifted. But understanding that, for example, this object itself doesn't have any obvious lift, and maybe it doesn't have a lift. It also maybe it doesn't have non-obvious lift at all. But
I didn't just I think question of whether
no, it's worse. I mean that theorem of Thomason about classification of like Karoubi-Dense subcategories, it works. It applies. We can apply it in the situations when we have not a homological homomorphism, but actually a evolution, like evolution by some subcategory. But here it's worse. I mean, the image of homological homomorphism in general might be not a triangulated subcategory, but its Karoubi completion is triangulated. But I can give examples, like kind of complicated examples when the image is not a triangulated subcategory.
So, just a block, but still, so if we just take vertex version and model of the killer it is a triangulated case.
Certainly.
And that embeds into your brain, and in what sense? So it's triangulated subcategory, but what is the problem?
No, I mean this is not a very motion. I mean, the point is that after we take incompletions, it becomes a
but the thing itself is not.
Yeah. And so yeah, when you have this homological motion, you can still prove that homological motion must be essentially subjective after direct summons, but Thomason's criterion doesn't work. For example, there might be some object with vanishing class in K0, which still cannot be lifted. So it's worse. Yes.
which still cannot be lifted.
Yeah.
So
Yeah, but let's.
so my naive way.
Yeah, yeah. But yeah, that examples are kind of complicated, so let's not focus on them now. So, but it will be important that, for example, such an object can be lifted at least up to direct sum.
Still there.
Yeah.
Does it follow from your?
It follows from this statement.
But okay. But still, you have to does the vector version quantum that you are now before in completion. Does it? It is a subcategory.
No, it's not a subcategory. For example, okay, consider another situation when you have this almost mathematical situation. And suppose that the ideal is contained in the Jacobson radical. Then there are no compact objects in the kernel, like also level perfect complexes. And there are no compact objects by Nakayama lemma. So okay, you can model out by the kernel, but you get the same category. Yeah. Right. Yeah. Okay. So, but now, like, okay, when we work with such general questions like trying to compute K-theory of this complicated limit, it's very useful to understand what we really need from this inverse system. So maybe try to formulate a more general problem, which then might be much easier to solve because you get rid of all the additional phenomena which it is here. And for example, you can generalize it to certain non-commutative situations. Yeah, because when we are talking about equivalence of spectra, we don't care that they happen to be infinity rings. That we don't care that there is symmetric model structure here. So we might as well consider non-commutative situations and just understand what we need. And let me give a definition, probably motivated later, but just to explain what kind of more general inverse sequences we can consider, so that we still have this good behavior inverse limit. So the definition, first let me give it for inverse sequence of rings. I mean E1 rings or DG rings, for example. And then for the dualizable categories. So let A1, A2, inverse sequence of well, let's say E1 algebras over some base ring K. Then the sequence is okay. Let's say strongly Mittag-Leffler, but
E1 is basically associated.
associated. The same as A infinity, or if K is just the usual ring, then you can then just DG.
So naively you can think of DG.
Yes, yes. Yeah, yeah. And in these examples, we can just assume that everything is linear. So everything is in the world of DG algebras and DG cases. Yeah. So it will be strongly Mittag-Leffler, and you can ignore the word strongly because I will not define the weakened version. So just the examples which I will be interested in, they will satisfy this additional strong assumption. But the assumption is the following. So if the two conditions are satisfied, so the first condition is that for any n, the inverse system of bimodules, so system an tensor an over L, where L is greater or equal to n, that this inverse system parameterized by L is essentially constant in an tensor an opposite modules. So basically in bimodules. And so more precisely, this is relative property Mittag-Leffler over the base K. This tensor product is over K. So yeah. So third condition is that this is like essentially constant, or also called the pro constant inverse sequence. So this basically means that if you take the actual limit and consider the differences between the limit and its approximations, then they form a pro-zero sequence. So there's basically the maps. You will have this vanishing of maps, sufficiently large indices. Yes. So this is the first condition, and second condition is that for any n and m, if we take this limit over L greater equal to both m and n of n tensor am over aa, so limit over L, then this guy is so requires that it is perfect as am module and also perfect as an module. Well, let's write an opposite, meaning that by default the modules are right. So this is right am module and left an. Yeah. So okay, it's actually not so easy to come up with the definition, and the reason I came up with it is because I considered like my more general picture coming from this non-commutative stuff. But yeah, suppose that we know that for some reason that this definition is reasonable. Yeah, again, I will probably motivate later. So basically, the example is this applies to the situation of formal schemes. But yeah, so first, okay, maybe just two remarks. First is that it is self-dual, meaning that an is a Mittag-Leffler sequence over K. Yeah, I'm dropping the word strongly, just pretend that this is Mittag-Leffler. So if an is Mittag-Leffler, then so is an opposite. It's self-dual, and second is that there's annoying detail that like it is not the definition depends not only on the pro object, but on a particular choice of approximation. So not only on the pro object given by the sequence, but it depends on a particular sequence.
So I would say that it's a parameter depends, but it doesn't depend on the
No, actually the condition depends. There might be different sequences which give the same project, which one of them.
This is the property, not of the proportion.
But of a sequence. Yeah. Like okay, more precisely, the first condition depends only on the project, and the second depends on a particular sequence. Yeah, I could modify this into a more reasonable definition, but it would just be more technical. So just to simplify this slightly, I decided to choose this version. Yeah, and in examples, it will be sufficient. Okay, so yeah, so example is that first example is that the sequence g of x mod x to the n is Mittag-Leffler over g of x. Yeah, and this is just okay. This can be computed explicitly. These are just certain Tor computations and how this procedure works. So it's not difficult. Leave it as an exercise. And using this and using basically QNet and base change, it follows that for any commutative ring, R and some collection of elements, let's say F1, Fn in R, the inverse system like R, but we model out like in the derived sense, meaning that we consider, for example, the Kashul complexes as the G rings, or in symbolical sense, it doesn't really matter. We model out by F1 to the n, different, let this be K, and we model out by 1 to the n, K to the n. So this sequence indexed by n is Mittag-Leffler over R. So this is basically just to take the tensor product of this statement, tensor power of this statement, and then base change. Yes. So yeah, and remark if R is noetherian and I is generated by elements F1, Fn, then this inverse system, let's say just inverse system of DG rings, assorted DG rings over R. So if you consider R mod I to the n, this is like as a pro-object, it is equivalent to the system of derived quotients by F1 to the n. Yeah, sorry, again, the F1 to Fk. Modeled by F1 to the n, so this is pro-equivalence. And so if we are interested in this, in example, dualizable inverse limits, it doesn't matter whether we consider this quotient or this derived quotient. Yeah, and for the second version, yeah, we have this Mittag-Leffler condition. And okay, this was definition for even rings, but let's formulate the categorical version like for dualizable categories, which is just straightforward generalization. Okay, so essentially the same concept. So if C1, C2 inverse sequence in dualizable categories, but now K-linear dualizable categories over some base, then we say that the n Mittag-Leffler, let me drop the word strongly, Mittag-Leffler over K, if so the third condition is that yeah, I need the notation. So the notation is that f mn are the functors from Cm to Cm, where m is greater than n. And then the third condition is that for any n, the inverse system f ln f ln right adjoint indexed by L greater or equal to n is essentially constant in K-linear continuous and the functors of Cn. And the second condition is that for any n and m, this limit over L greater or equal to m and n of FLM FLN right adjoint. So this limit like is strongly continuous functor from Cn to Cm, and it has a left adjoint. It is just a straightforward generalization of this concept for equivalence. Yeah, and yeah, and then in this generality we have this so non-trivial result that the statement about homological dimorphism works in this under these assumptions. So if Cn Mittag-Leffler complex, then we have short exact sequence 0 to the light of the inverse limit Cn, so in completion of the usual limit of counter-represented object of Cn to in completion of the limit of continuous solving categories. So have this big general statements using this condition. Okay, and so this was the first characterization in terms of limits, and accumulated the property like what does it mean that it is actually very well behaved. This limit is very well behaved. So another point of view, which is actually also useful, is using this dualism internal home. And okay, so so let me first formulate it in the case of formal scheme, and then formulate generalization in the same spirit. Theorem about nice behavior of dualizable internal form is the following. Okay, let me just to make this a little bit shorter. Like here, I formulated the statement in terms of short exact sequence, but this includes the statement about homological epimorphism, just by definition, right? So let me formulate this in the same spirit for the dualizable internal form. Let R Noetherian I deal in R. Then we have short exact sequence. The dualizable internal form, which is also the same as the nuclear tilde category. So dualizable internal form from I-Clausen derived category are DFR goes in completion okay, let's say in this case, let's say functors, linear functors from perfect Clausen are modules to counter-represented objects of the author. And then it goes to in completion of functors from perfect Clausen are modules to countable Clausen category. So it is a very similar statement, and In fact, it turns out to be essentially equivalent statement to the previous theorem about dualizable inverse limits. But let me, of course, I should make a remark, a general remark about how the dualizable internal forms work. They are they have similar level of complexity to sequential inverse limits, and so general remark is that. And let's for simplicity restrict to commutativering categories. So if we start with small categories A and B over some base.
Yeah. So you formulate two theorems. Then what's the plan? Is it to prove them or
I will formulate. Well, first I will formulate an abstract version of this in the non-commutative setup, and then I will. Yeah, and then the third result will be in the context of rigidification, and then I'll just try to explain that this is like essentially the same phenomenon in different situations, and roughly speaking, how this is proved, and then we will be able to compute K-theory. But first, I just wanted to explain.
So I didn't quite understand.
Yeah.
Are we going to prove the theorems or
I will sketch the proofs of.
So yeah, you will sketch them.
Yes, the proof of all of them, but specializing maybe to one of them, because the proofs are very similar to each other. Yeah.
And what is the role of the remarks? It's kind of it will be something relevant for this. Maybe for explaining the difficulty. What's the?
No, this remark is just about how dualizable internal forms work, because I didn't yet mention it.
So you just mentioned that they exist.
Yeah.
But and how, when you say how they work, how to compute?
Roughly
How to compute?
Yeah.
So for instance, so you explained last time that how to compute
Inverse limits. Yeah.
How to compute inverse limit when the word compute is understood. And now you are saying that for internal forms, again, a recipe, but not quite.
Yeah, but not quite effective way. Yeah.
So, so is this theorem? Is you also put this theorem for any proper TP category?
Well, that's what I'm going to.
Sorry.
Yeah. But first remark without any assumptions on source and target, but just let's say commutative for simplicity. So suppose we're starting with small categories basically, but linear over some base. Then the dualizable internal form is dualizable internal form K linear from end of A to end of B. This is the dualizable kernels of the following. So take the functor from incompletion functors from A to countable incompletion of B. We go to incompletion of functors from A to countable colimit-preserving. So in particular, if this A is like perfect modulus over some algebra A, like algebra R, then here we're taking representations of this algebra in the countable incompletion of B, and here we're taking representations of this algebra in the countable colimit-preserving. And in general, so this is just some functor, and we don't have any control for the dualizable kernel, so it might be quite nice abstract situation. But now, so now first I should recall the general concepts due to Kontsevich of smoothness and topology. The case, but let me do it in a non-standard way, so that it works for the dualizable case. So C in like dualizable category linear over some base is so first.
Well, it's a dualizable. Well, so it's not quite Kontsevich. It's in the spirit of Kontsevich.
Yeah, but I would say straightforward. So first is it is smooth if the coevaluation functor from K modules to C convex dual over K is strongly continuous, but this just means that coevaluation of K is compact object. So this is like the statement that the diagonal is compact, just the usual notional smoothness, and it's proper if the evaluation function from T convex dual K to K modules is strongly continuous. In this sense, they are kind of, well, in some sense, they are dual to each other. One is related in terms of coevaluation, the second one in terms of evaluation. Okay, remark if so if C is the case of K modules, some K1 algebra over K, then C is smooth if and only if A is perfect as a bimodule over itself. Yeah, everything is like all of these are of course relative properties over K. So it's proper if and only if A is perfect as a K module. Okay, now so I can formulate the general statement about the level of kernel forms.
And for instance, if
Yeah.
so, for instance, suppose that C is. So I'm curious about this notion,
Yeah.
because I'm not sure that I will be able to understand the rest. But this it's introducing such a notion looks like a good idea. So I'd like to understand what this really means in some kind of, for instance, suppose that C so category of sheaves on a locally compact space.
No, but I mean, this is not.
Maybe in this case, it's not realistic to expect.
No, this is actually interesting example. I mean, it doesn't have a chance to be smooth for non-trivial spaces X, but it can be proper in this sense. And this means like a good local behavior of the space. So it means that the compactly supported cohomology factor is strongly continuous. So upper street from the point is continuous.
And this is what its properness or smoothness?
Properness. And smoothness almost never.
But in particular, so you are saying that if, for instance, if locally compact space is smooth.
Yeah, like a smooth manifold. Yeah.
So a smooth manifold. So interesting. So you are saying that the category of sheaves on a smooth
Yeah.
manifold.
Yeah, the
Topological manifold is proper, but usually not smooth.
Well, I would say almost no. Unless zero dimension. Yeah.
It's proper.
Yeah, and of course the statement. Sorry, the standard examples for separated schemes finite type over a field, and then it just reflects the usual notion of smooth and proper. Okay.
Properly, so what you need is something like local contractibility.
Yeah, but it may be okay. Yeah, but local contractibility, but in this sort of in the weak inappropriate thing. Yeah, okay, so now the theorem in this more general non-commutative context is the following. So following results. And okay, let me formulate it even for not necessarily completely generated categories. So let C be a dualizable proper category. Yeah, proper over some base K. And suppose that we have the following condition. Suppose that correlation of K, the diagonal object, is counter-represented. So it's we don't require it to be compact, but we just want it to be at most counter-represented. Then C is internally projected. So I'll explain what this means. Internally projected in dualizable categories over the base. So it just means very nice things. So dualizable internal form from C to some short exact sequence is again a short exact sequence. And part one and part two is actually a corollary of this, but let's just restrict it to
also K.
yeah, that's right. And second part, let's just formulate again for simplicity for in the computer generated case. So let's so if moreover C is computer generated, so it's in condition.
When you say dualizable proper, it means it's proper and being dualizable.
Yeah,
space.
yeah,
So I would say proper dualizable.
I don't think it matters.
No, well,
So if moreover C is computer generated, so this just means that in this case of compact objects we have perfect. So K modulus of morphics are perfect, and the triangulated category A is generated by mod count of many objects. So this is my condition. Okay. Then for any.
so what does it mean that FK is
Yeah, okay, let me.
So a priori it lives in C tensor C check.
Yeah.
And you want it
To be a one gallant compact. I don't want that diagonal to be too large.
Yeah. Get the one.
Yeah. If it is computer so then conditions, the above conditions mean that like the models of morphisms are perfect for any in X and Y and A. And it also requires that A is generated as a triangulated category. A is generated by at most count of the many objects.
Right, with item.
Sorry?
With item.
Yeah, generated. Including taking retracts. this is just the translation. So first condition is translation of properness for completely K-theories, and the second, assuming properness, the second condition just means exactly that the relation of K is countably represented.
So what does it mean in real life?
In real life, you can just think that we are talking about.
Suppose that A is quasi-core. What?
Yeah, then just X should be a proper scheme.
And what about this contability?
No, that's generated by single objects, in particular by countable menu.
So, but what is this?
No, I mean just the statement itself applies to situations when it's not necessarily like, so if being generated by one object is the same as being modules over some algebra. And this just a priori, it's a sufficient for me that there are countable many generators. Yeah, but in practice, we can just think about examples where it's modules over a program. And so under this condition that it's completely generated with satisfying this property, then for any B, just for any category, translate stable infinity category, K-linear stable infinity category over B over K, which be complete. We have that. So we have a full exact sequence. The level internal form from end of A to end of B to incompletion of functors, K-linear functors from form is also K-linear. Yeah, K-linear functors from A to countable incompletion of B, and then to incompletion of K-linear functors from A to countable fucking category. Yeah, the number of brackets. Yeah. Yeah. So in particular, this includes the homological equimorphism statement. So when we go from this category of functors, this category of functors, homological. Yeah. So this is kind of an abstract non-commutative generalization of that theorem about forms. Okay, and so both results about the internal form and about limits of Mittag-Leffler sequence, both of them are complicated, but they have similar levels of complexity. And I will explain roughly how this works, how this is proved, but first I want to explain something about the third characterization of nuclear category, which is commutes one using registration. So first, in this case, first I will explain how a general registration works without any assumptions on the symmetric model category. So kind of general construction. Let's see presentable stable symmetric monoidal category. Yeah, by default, I assume that tensor product commutes with colimits in each argument. But I don't assume that the unit is compact. This is not required. So if I take any presentable stable symmetric monadal category.
So then, so is it? Symmetric monoids. So all
In the algebra, in presentable categories. Yes.
yes. So in this world,
Presentable categories.
presentable stable
Yeah.
categories, there is a notion of monoids, let's say,
In the algebra.
Yes. Yeah, that's.
And it's symmetric one.
Yes. Okay. Let's just write it. Yeah. Symmetric monadal category. Then this realization can be defined, constructed as a certain full subcategory.
So you gave some kind of definition of rigidification.
Just as a right adjoint functor to the inclusion of rigidity into all presentable symmetric monadal.
So you are saying that rigidity is a property.
Yes.
So we have an inclusion, and then the rigidification is the
Right adjoint.
And now you explain why it exists. and
Well, how to
construct
construct it?
maybe
Again,
for all the reasons, something for general reasons, but how to construct.
Yeah. Again, semi-explicit. Okay. So it is a certain full subcategory in the incomplete of C, and it is generated by formal colimits of functors from the whole set of rational numbers to C, such that for a smaller than b, the map from phi of A to phi of B is straight class. So it's sort of similar to that representation of dualizable kernel.
By the way, it could be from the notational point of view, it could be principle to some notation. So it's often useful to consider following category notation marks objects on C, but most essence are in the case.
Well, this is not a category because
This is not a category because it's no. But anyway, so it's often used to consider this.
well, it's ideal. I would say that it's kind of a two-sided ideal.
And then you could just say, and you can consider simply you can say Q and strict. Then you just consider morphisms.
Well, yeah.
And by the way, is it true that from Q is the same as morphism from real numbers? Because
No, I mean it's not the same, but
not the same, but by continuity, I mean.
I'm not requiring that it commutes the phi commutes with fixed commutes. But I could also require it. It doesn't really matter because I can replace such a functor with another functor, which an every rational number equals to the colimits, and it would not affect essentially anything.
And suppose that you take instead of Q, you will take maybe not just positive integers and would such inductive limit actually lie in?
In fact, that's the problem. That is the problem. That in general they would not lie. So I mean, in general,
You need infinite.
Yeah. I need to be able to decompose any of this morphism into compilation of two and then into compilation of two. Yeah. So, and this is not automatic at all.
And maybe is this the reasons why continuous functions?
I don't know. Well, maybe yeah. But in that case, also when we have this way below relation, yeah, we can insert elements.
I mean, is there some way of saying this? Like you look at, right, so you look at the ideal of trace class maps.
Yes.
Then you look at like the square of that ideal or something.
Yes.
And you look at the intersection of all powers of that ideal. And then you take in this one.
No, well, okay, you can put it like that. No, but it's not just in the intersection. I decompose it like one trace class map into compilation of two, but then each of them. So it's more tricky. But okay, but basically, if you are able to decompose any trace class map into compilation of two, then you can produce such a refinement of an n-index diagram into Q.
So you basically need an ideal of morphisms that's contained in the trace class maps, and such that the ideal squares to itself, and that any map in the ideal.
Yeah, and you're talking about ideals in this naive sense in the commutativering.
Yes.
Yeah, then it's true. Yeah, if that happens, then we don't need the Q-index diagrams. We need only the n-index diagrams. Okay, that's true. Okay, so that is so this is the general situation, and as you see, this might be very tricky to describe explicitly because these Q-index diagrams are quite complicated. But now there is also a notion of a good behavior of this realization. And let me introduce this auxiliary notion. Definition. Let the
Let's just trace class.
yeah trace class.
So it's a property of morphisms.
Yeah, in C, yes. Of morphisms in C.
It's a property which is formulated in terms of.
Yeah, in terms of dualizable internal form. Sorry. In terms of internal form to the unit tensor. Yeah. So if we have some completely generated category, completely generated symmetric manual category, and assume that the unit is compact. But I'm not even requiring that the tensor product of compact objects is compact, but you can assume that as well. Then X in D is called nuclear if for any compact object Y in D. Okay, there are different ways to formulate this, but let's just formulate it as follows. The map from internal home from Y to the unit tensor X to internal home from Y to X is, I don't know, or equivalence. So this is kind of the concept of nuclearity of objects.
This, because we are not so far from the classical, so there is some hope to understand.
Yeah.
So for instance, first of all, since the category equation is generated, you can try to think perfect. However, I think it's product, the tensor product of perfect objects is not required to be. Yeah, of course, objects is not required to be.
Let's actually assume that because it will be sufficient.
Okay. On the other hand,
there are then you are saying that this still the notion of nuclear functions.
And is one axis compact? Is what is called necessary? No?
No, this is the assumption. I mean,
So if we assume that the tensor product preserves compactness, then just forget all the test, then we just have an abstract.
yeah, but as Sasha mentions, this is actually a condition because you can consider, for example, representations of a finite group of a field of precession P dividing the order and okay, that's product of
It's just well, the tensor, the property of the tensor product preserves. And let me think about. Let us think about two examples. For instance, suppose we have a group, an algebraic group G, maybe a group scheme, and since you want symmetric, that is let it be. For instance, the editing. Then I want convolution.
yeah.
So we can consider quasi-core, and then we can consider the character of D. And the models I want to consider. Well, not from. So this is this quasi-core is not convolution. So, but well, it's completely generated, but the convolution
The
doesn't.
condition is not necessary.
The convolution
Yeah.
doesn't preserve. But still, we are in your. Then, what does it mean for a quasi-core shift to be?
I think it's in this case it's okay, maybe it's not so easy to say. Yeah. Okay, at least from the top of my head, I cannot immediately give the answer, but I would say that this is not the most natural.
No, but but then, I'm trying to problem with that. It's difficult for me to swallow many abstract definitions without getting, so to say, the church. So if this is not a good example, or it is not a good example thought about, then maybe we could look and give some.
Well, I'm actually going to explain a class of examples which are in which this behavior of rectification is really good. So, which will include, for example, P-complete abelian groups or I-complete R modules, and also representations of finite groups as well. So. Yeah, so we have this sort of
Just know that the format of definition just have an abstract terms. Technically, you can still and a subcategory that still ask. So for any semantic map.
Yeah.
And
but I'm taking this.
and then you require things to be homomorphism for a certain class
Yes.
of objects.
Yes.
In this, but in your situation, you and this notion of nuclearity, does this notion of nuclearity has anything to do with the notion of nuclear, what you call that, with some previous notions of
Yeah, I mean, in the framework of condensed mathematics, it is actually closely related.
And what about Clausen introduced nuclear spaces, which are what nuclear biological vectors.
Yes, yeah, maybe nuclear. Well, he was mostly considering, I guess, nuclear pressure space.
And does his notion of vector have anything to do?
I mean, it's not a special case, but it's morally very closely related. It's, I mean, both. Yeah, I mean, he also considered conditions of the same form, but it wasn't purely algebraic. Yeah, but okay, these conditions like really abstract, but it's like mimicking the Grothendieck definition of neutrality in functional analysis. Yeah.
So I guess this means that any map from a compact object into X
Yeah.
is automatically trace class.
Yeah, but that's just taking pi zero. Sorry, pi zero of maps from the union.
This is the stronger.
Yeah. Well, but in fact, sorry, this is equivalent. You can also formulate this just by requiring that any map is trace class. Okay. But I chose just this way to say that just the internal home itself can be expressed in this way. Okay, and then yeah, this nuclear object condition. Position is that in this condition, so under these conditions, denote by nuclear of D, the full subcategory. Nuclear objects, then nuclear D is generated by colimits of sequences x1, x2, and so on, where each xn is compact, and each map from xn to xn plus 1 is split class. So for this nuclear subcategory, we have much more precise crystallization. We don't need this diagrams indexed by Q, and need only the sequences of trace class maps. So all such objects are nuclear objects of this sort, of this form, and every other nuclear object is actually omega-1 filtered colimit such.
Sorry, does this require that the compact objects are closed under tensor form?
No, it doesn't even require that. Yeah. But again, psychologically, it's convenient to assume this. But this condition is violated when you consider, for example, this liquid vector spaces. Yeah, it's Archimedean. Yeah, but in our situation, yeah, okay. So, and now this theorem is the following. Yes, first, yeah, okay. So let's first introduce the definition. Symmetric monoidal K-theory is well, I like to call it locally rigid, but K-theory and Rosenblum call it semi-rigid. But mean, I guess both choices are good, but locally rigid kind of more intuitive. It's kind of conceptually close to locally compact spaces. If first of all, C is dualizable. Yeah, and again, I'm giving a definition which is slightly different from this Gaussian-Rosenblum definition. C is dualizable. The multiplication functor from C tensor C to C is strongly continuous. And the third is that compact morphisms in C are contained in trace class. So compactness of a morphism implies that it is trace class. And actually, assuming the first two conditions, alternative way to say this, so 3 prime, so to say, we require that the right adjoint to the multiplication from C to C tensor C is C tensor C linear. It is automatically Lux linear because it's right adjoint, but it's required that it is linear. So after this such a definition, I am supposed to give examples to clarify what this means. For examples are I complete the derived category over a commutative ring. So actually, we take any commutative ring and any finite generate ideal. For this first example, second is just representations of finite groups over some base. And third is sheaves, let's say with values in D of Z on locally compact Hodor space. Yeah, in each of these cases, it's not difficult to verify. And basically, so for completely generated categories, it's just saying that compact objects are dualizable and compact objects are rigid, and the tensor product of compact objects is compact. But the unit is not necessarily compact. Yeah, okay, and now I can formulate what does it mean that verification is well behaved. So okay, I'll start with actually an abstract formulation. So let C be locally rigid such that the unit is counter-represented. So as you see all the time, I have this counter-representation condition on some crucial objects, and this will be actually very important. Otherwise, all the statements they would be wrong. Yeah. So assuming the local rigidity and counter presentation of the unit, then for any object M of C. So the object, so we can define the object M trace. So the object M trace in of C given by the condition that maps from Y M trace are exactly that spectrum of trace class maps from Y to M. So from 1 to internal home from Y to the units and the M. Is nuclear. Object M trace is nuclear. So the meaning of this condition is that under this condition, the functor M trace plus M to M trace defines right adjoint.
What is the end? Can you finish formulating this?
Well, I am sort of including the consequences of the statement into the theorem.
The orbit given by this is nuclear.
Yeah.
This is already a state.
Yeah. Yeah. Let's put it like this. Yeah. So this is a theorem, and this is corollary. That under the above conditions, the functor going from M to M trace defines right adjoint to the inclusion of nuclear objects in of C to in of C. And nuclear of in C is exactly the representation of C. So in particular, so yeah, so first statement,
And what is
this is just was the general notion of nuclear objects in the complementary case.
So the definition of nuclear object didn't involve the tensor structure.
No, it did.
It did.
But in completion of symmetric model of K-theory is again symmetric model of K-theory.
And then to have a notion of object. And then so you are saying that this so this is the description of it. So what's the model? So in this case, you can describe city.
More explicitly, yes. And so in particular, so in this case, C rigid is generated by n index elements of space cosmos by formal elements sequences x1 and so on are maps sample one with space class. Yeah, and in particular, this applies to the situation of a formal scheme. So,
You say that an object MCR is nuclear, you mean nuclear as an object in the C. Right?
Yes. Um, in
At
particular,
some point, we need a break.
yes. Yeah, I can just formulate the special case for formal schemes and then we'll make a break. So we obtain basically the statement that registration of the category. So if they are theorem I ideal in R, then registration of this category I complete derived category is given by nuclear objects in the incompletion of the usual actually of this category itself. So the nuclear object in the incompletion of the I complete derived category.
Now I forgot, this registration was had a name. So I.
Well, I sometimes call it
you gave at the end of your last talk and at the beginning of this talk,
yeah.
you gave three different but in fact equivalent definitions of something which is called
You
and one of them was that you take this registration.
Yeah. But now this nuke is just saying nuclear objects in that.
And now you have this theorem describes it more explicitly.
Yes. And okay, then after the break, I'll kind of briefly sketch how such complicated statements prove. So very rough idea how it works, and then explain how this allows to compute K-theory.
And is this indeed so on the one hand, this kind of description of
Mhm.
the other hand, so if you just unravel the definition of the object in this particular case, just want to get understand what the question.
It's still not so easy to describe like geometric collection of objects, but it's easier to describe the subcategory which is original version. Which is certain like almost category, certain non-commutative version of. I mean, it's okay, it's commutative, but you use the non-commutative version of almost mathematics.
Okay, now we have.
Okay, so yeah, I explained three approaches to this nuclear category, and in every approach I explained was it that this situation for formal scheme is particularly well behaved, and okay, I will not prove like all the statements, but I will just. The proofs are sort of similar, but I'd like to explain just in this particular approach using registration what this good behavior roughly means. So So consider this assumption. Consider category C, which is locally rigid. Yes, C with the product. Locally rigid symmetric model category, and such that unit is counter-represented. Then, so okay, so this nice behavior of rigidification, so it can be translated into the following. So translates into the following. So for any, so I will write a formal statement and then explain the intuition. So for any object of C, let's even not put any nice conditions on them. Just take any pair of objects and we take the following. So consider maps from C from map from the unit to something dual tensor Y, where let's just put here that dual means internal font to the unit. So it's also called pre-dual. So something dual tensor Y, and now it's slightly confusing. So I'm considering as a contravariant functor on the category contravariant functor on C to spectra, but I'm restricting this to C omega 1. So okay, so what is written here? So just consider this. Pretend that C omega 1 is kind of a ring, and this is like a right module over the string. So more precisely, this is contravariant functor to spectra on this case. So as I mentioned, like contravariant functors to spectra are the same as split objects. So this is one mathematical object shaded with object 1. And another thing is we take also map from the unit to X dual tensor the argument. So this is covariant functor to spectra. So this is like left module over this category, or in other words, object of the incompletion of the opposite category. So the tensor product is tensor product of right module and left module. Also, it's evaluation, if you want. I consider this. So this is some spectrum, very huge spectrum. But the statement is this is just the same thing as so that it maps isomorphically to map from the unit to X dual tensor Y. So okay, intuition. Like the ideal of trace class maps equals to its square in the direct sense. So if you take this ideal, if it's square, then it equals to itself.
And why is this intuition but not statement?
No, I mean, okay, trace class maps. This is like a property of a morphism in a homology category, but okay, you can make it into a more precise version of an ideal when you have like okay.
Because just one, because the question is what is an ideal derived?
Yeah.
So if we want to have quotient, then
I didn't, and I'm not going to.
and you are not.
Yeah.
So So, yeah, more or less.
Yeah, more or less. Yeah. But this is like a formal mathematical statement. That is, I'm not saying that it's easy to prove, but at least this is some statement which you might try to prove, and which is
So this is an additional property of, so given relations.
Yeah. how to represent it.
Presented, then you formulated a certain property.
Yes.
Additional property.
Yes.
And now you claim that in your situation, this property.
No, I'm just saying that for any such locally rigid case, you can say that the unit is counter represented. This holds. I just translated the nice behavior into this, but I previously said that this nice behavior always holds. Yes.
So it's, or I don't, is it a theorem or what?
Theorem. So nice behavior was a previously formulated theorem somewhere in here. Yeah. So this was a nice behavior of the verification, and I'm just translating it into a formal statement. Okay, equivalent formal statement about this ideal of right class match.
How far, so is it a reformulation?
Reformulation of it. So nice behavior just refers to this theorem.
So also, so is this, would the statement be true with X dual replaced by any alternative C?
That's what I was going to say. Yes. Yeah. So. Yeah, okay, so in fact, following folds. Following a very strong statement folds. For any, well, okay, I'm just replacing the X dual by some object Z. So for any Y and Z in C, map from units to something dual tensor Y. Then for kilometer one, map from the units to Z tensor something is isomorphic to map from the units to Z tensor Y. So this is a very strong statement, but in fact this holds. And okay, the proof is like really complicated, like more complicated than what happened yesterday with 86. But let me first mention the elementary envelope of the statement, which might be helpful for understanding this phenomenon. So elementary envelope, there is this analogy between certain topological spaces and this rigid or locally rigid category. Elementary envelope is the following: if X is the locally compact Hausdorff space, countable at infinity, then X is normal. So for any closed disjoint subsets, you can find disjoint open name. Usual notion of normality of the topological space. And yeah, and this elementary statement is of course not hard to prove. For example, you can prove that it's power compact and power compactness implies normality. Yeah, but anyway, like you prove it so to say, you prove it using the fact that space has points, and you can think of it using a step with some additional structure, do some manipulations, but you're not thinking about such problems in terms of the category of open subsets. Yeah, and roughly speaking, here we are forced to. We don't have any kind of analog of notion of a point of the space in this completely abstract setup. Yeah, and roughly speaking, here we are forced to deal with such problems directly, and so I will just very briefly explain how such a computation can be done. So, yeah.
So it seems that theoretical topology becomes a hard science.
At least on the level of analogy. Yeah. So, okay. So the idea roughly is that you can approximate the unit by a sequence of pop-up maps. So unit object is colimit of some, let's say, M1, M2 on, or very close. Then you also choose approximations for Y. Okay, I apologize for this Y, which is like the same Y which is used in I-adic, but that Y will be like capital Y hat. Y, so you write this as a formal colimit of yi, and Y hat of Z is a formal colimit of ZG. Then, yeah, you can try to compute the tensor product by expressing both functors as fixed colimits of representable functors, and this is difficult to explain, but I will just say which fundamental facts of life you are using in terms of how you can permute limits and colimits. So there will be two basic facts, one of which is easy to understand, and the other one is it looks like it's AI generated, but it's like what you encounter.
So when you say, is M9 and M9 plus 1 compact?
So one me?
Sorry? Is this, are the transition maps generating 1, are they compact?
Oh, yeah, you're right, of course. Sorry. Yeah, I assume that's a compact. So I could also write. I could also say that I'm taking y hat of the unit. Yeah. Let's just put it this way: y hat of the unit is a formal colimit of this sequence. And then you can just assume that maps are complete. Yeah. Okay, so we're using two facts. So fact one, that let I be directed password set. And F is a functor from natural numbers with the opposite order cross Y. Let's say two spectra, but the target can be any completely assembled category. Then, when we do this, when we take the sequential limits of colimits by F and I, so this can be rewritten as fixed colimit over all maps, order preserving maps from natural numbers to I. of inverse limits over n less equal to m f of n phi of n. So where this set of pairs n less equal to m is considered as a subset of n opposite percent.
Is there a way to it vector? Is this something is called
Not really, not really, yeah. But I would say that this is basically an application of AB6. So yeah, here I'm just using the AB6 for countable products and the commutation of fixed colimits with finite limits. That's
okay. If I replace this vector by sets,
yeah.
then this becomes an axis.
Yeah, become an easy exercise just to compare the elements. And it's quite intuitive. You just write down like on which stage you are able to realize it. Yeah, so this is kind of an easy fact. But the second fact is much more tricky to understand. So, so let's I and J be directed partial sets. And now we have we take functor of 4 arguments and opposites cross and opposites cross I cross A and again in functor to spectrum. And then we make 2 assumptions. You that when we take the limit over J, limit over J, limit over N, limit over I, f of n k I j, considered as inverse sequence indexed by k. So this maps naturally to the limits over n, colimit over I, colimit over j, f of n k I j. Again, this is inverse sequence indexed by k, and I require that this is pro equivalence. So this is assumption. This is not the conclusion. Yeah. So this is the first assumption. Second assumption is that the same thing with I replaced with G and N replaced with K. And now the conclusion. So if you assume this, then the limits, inverse limit over N, colimits over I, colimit over G, f of n I G is the same thing as colimits over maps from natural numbers to I, maps phi from n to I, colimits over map size from natural numbers to G, limits over n less equal to m, limits over yeah. A limit over k less equal to h, f of n k phi of m psi of m. So this is the conclusion from this. Yes. So I mean, after this is formulated, I mean, it's not so difficult to prove actually if you just sit down and.
If you understand the state.
Yeah, it's not like after you understand the element, there is some.
There is some still.
Yes. But that's that's exactly what you need in order to prove that statement about standard product. About the statement that the trace class maps square to themselves as an idea. Yeah.
So, where are we now? So,
Yeah,
what was the goal, which goal?
And now I'm going to no I roughly explained what does it mean that all these approaches to nuclear modules like in all these approaches we were in the situation where the corresponding construction is very well behaved, like the limit, the internal form, and the rectification. And now I'm just going to explain how this nice behavior allows to compute K-theory. I mean, give a sketch. Uh, so theorem is the following, like in this kind of lecture situation. Let's so A1, A2, the inverse sequence of stable infinity integrals. And now we just assume that complicated statement about homological epimorphism holds.
Which
I will formulate. Assume that the functor from countable incompletion, the functor from the limit of countable incompletions of n to the limit countable commutativering of n, that it is a homological epimorphism. So previously I explained that in the situation we are interested in, this condition is satisfied. And again, the level of complexity of this statement is kind of similar to what I sketched here. So assume that we just know that this statement holds. Then I claim that K-theory, continued K-theory of the dualizable inverse limits of incompletions of n is equivalent to the inverse limit of K-theory of n. So we have a natural map and statement that it is equivalence. Okay, so let me briefly explain the ideas. So what would be the natural way to prove such a statement? So we have the usual exact triangles. The exact triangles starts from the limit, then goes to the product of K of n, and then again the product K of n. This is exact triangle or fiber sequence.
Can you give a sketch of
I very briefly explained how the idea of the proof and the main steps. So so we have this exact triangle. That's basically how the sequential limits can be computed, so we want to somehow categorize it. In such a way that we will be able to conclude that K-theory is indeed the limit. So now, so to clarify, roughly speaking, constructing a short exact sequence of K-theory. So now there are a few ideas here Yeah, and here I'm of course here, let me mention here that I will be certainly using the fact that this is the same as K-theory of the product. Again, this statement I explained in the previous lecture. Yes. So now the main ideas are the following. Given this, given such sequence, okay, like I don't even now I'm not even assuming that this condition is satisfied. So given say some another sequence dm and this functors, so it's inverse sequence, and I'm denoting by fmn the functors from dm to dn. I'm going to put we have we have this O-Plux version of a limit. So this is a very natural thing actually to consider. Yeah, well, this is basically like we consider a sequence of objects xn and dn or n, and basically the maps, let's say phi n from xn to the image of xn plus 1. So the limit is certainly contained here because in the limit we require identifications, and here we just take the maps. So intuition is that this is like a category with a semi-orthogonal decomposition into all of this Dn, but it's somehow completed version because each object, usually each object has some say finite filtration with subquotients in the semi-orthogonal summations, but here it's infinite filtration. But still, one can prove the position that just K-theory of this Flux limit. Yeah, and there is a generalization to other localizing invariants, but let's just consider K-theory. So this is yeah. So I mean, it is the same as K-theory of the product, which is easy to prove, and then we know for non-trivial reasons that this is the same as the product theory of the. And the statement that it is the theory of the product is roughly, let me give just a sketch, but it's easy to make it precise. So let's just consider K0. So take some particular object, xn phi n in this O-Plux limits. And what we want to do is show that the class of this object in K0 is just the same as the class of an object where we have the same xn, but zero maps between these guys. So we just replace all of the maps by zero maps, and we want to see that the resulting objects have the same classes. But this is kind of an exercise for meta-linkers, so to say. It's just writing down a precise way, precise like exact triangles to identify these classes. So basically, you can define this and the functors. So gn, okay, so gk. Computed on this xn phi n. So this is, let me write it down in formula. I'm just removing the first several objects and then consider this all the rest, xn, xn plus 1, and so on, with the same transition maps. And then Yeah, and I also have this delta t from Dn to the flux limit. Sorry, from Bk to the flux limit. So delta t x is just I'm putting zeros everywhere except for the case position. And then we just have exact triangles. Gk plus 1 goes to Gk, goes to delta t. So exact triangle. And this implies that we have a well-defined exact triangle that direct sum of, let's say, over k, direct sum over k greater than equal to Gk of our object xn pi 1. So direct sum over k greater than equal to 1, Gk our object. And we get the direct sum of this delta t of our object. But the direct sum of delta t is just the object with the same xn, but with zero transition maps. Yeah, yes, so these particular infinite direct sums are well defined, and we see that they're different just by the sum on G1, but G1 is an identity. So G1 is identity. So you directly see that this object has the same class as this object, and then you just apply the same argument, but you consider not object but just identity functor and certain idempotent and the functor, and they have the same classes and the functors, and in this way you just deduce this statement. The K-theory of the flux limit is K-theory of the product, which we know to be the product of K-theory. And so this is the first idea, and then then we want to apply it. Basically, because we have this, because of this homological statement, computing K-theory of the dualizable inverse limit reduces to the computation of the usual K-theory of the usual limit of counting categories. And now there is a following way to proceed. So we consider this limit of counting categories, which, as I mentioned, is very complicated. We can embed it into O-flux limits of the counting categories. So this is kind of the beginning of this simplification, where embed the limit into O-flux limit for which we know that K-theory is just the product. Well, up to shift. But the problem is that the quotient of this by the image of this is very, very complicated. Like you cannot control it. I mean, but even after you use all the tricks with limits and limits, it's just impossible to control the fiber of this map. But fortunately, it's possible to simplify this. So you can consider the limit, this incompletions, countable ones. And here you consider this more naive thing, which is the O-flux limit of incompletions, which were modeled out by the O-flux limit of A. So we have this commutative square, and this arrow induces equivalence on K-theory because of what we already because of this statement. It would be nice to replace this Laplace limit with this one, which is in fact much more controllable. Unfortunately, so the proposition is that there exists a unique error this, which makes the diagram commutative. And this is another crazy computation with limits and colimits, which I will not explain, of course, but it can be shown that such error exists. Then, so we are reduced so after we know this, we're reduced to proving the following. When we take the double quotient, so we take complex limits, countable completions, we mod out by the complex limit of an, and we also mod out by the actual limits of this incompletions. And so basically we want the K-theory of this is naturally equivalent to K-theory of the product well after shift, K-theory of the product of an shifted by n. And then with certain efforts you can prove it in a similar fashion, but more complicated version of this. So this can be done, and this somehow allows you to construct the desired multiplication of this exact triangle after shift. So that's roughly the idea how this works. Commutation of K-theory with limits in this. Okay, I think almost no one survived. I think it's a good time to stop.
So my understanding, you
Yes, another one, yeah. And that talk will be actually about mostly about small case grids, but kind of a smart way to deal with them.
not going to.
Yeah.
So can we meet on Monday at 4? Not many of us. And by the way, does your Monday, does your next talk rely on
What? No, there will be some. I will mention the connection between the dualizable internal forms and this motive, but I will not use it in essential way. But
so anyway, next. So we definitely need one. Can we meet on Mondays at 4:30 in room, the available room? Arrives and 358.
Unavailable? What? Is this one not available at that time?
At least, the problem is that now, Ryerson 358 is available in officially And I didn't make a reservation for a big room. However, if it's available, then maybe it's, are you saying that for your,
For the purpose of recording, Ryerson 358 is not.
the Ryerson 358 is not.
This is a very good report. But I can check on Monday morning.
Yes.
Part of it.
So then what can you then check it on Monday morning? And so if it's if a big group, well, the problem is not with size, but with
Recording. If we do use Ryerson 358, I'll just get the text.
So if there is a better room than the Ryerson 358, then it would be better. And if not, then what is the next? So we have some room, maybe this one available on Friday. But I'm not sure. On the other hand, on Wednesday, we will
The column.
we'll be giving a column.
Yeah, Wednesday.
And on Thursday, Louis talk. So is there a chance that something is available on Tuesday?
There certainly might be. I sorry, when you say something, you mean like one of the, like a room that records well.
But also there are some other events. There are some other events.
Yeah, and if worse comes to worse, and we don't have anything on the Ryerson 358, I suggest we still go to Ryerson 358. I'll just call the tech person to make sure that weird image doesn't pop up on the screen.
Okay. So then the arrangement is that we definitely meet on Thursday at 4:30. But the room on Monday and 4:30. But so the default room is Ryerson 358. But there is a chance that there will be a better room. So then please notify me. Or maybe just please notify me on Monday morning about the situation, and then I will send an email to you.
Also, do you know what time the front opens? Like what time the office? I think it's not open. Maybe it's early.
8:30, but not.
8:30 open. Well, I be healthy for me to wake up early. 30 minutes.
Maybe 9 to be safe. I don't know.
Sure. I don't think, if it's been reserved, it's not like the
Yeah.
30 minutes.
Oh, yeah.
Are there any questions? Let us study this.